As the temperature of an object increases, due to the increased kinetic energy of the atoms and molecules, the average separation between the atoms and molecules may increase. So this can happen in solids and liquids. And as a result of that, we can see that the dimensions of the objects increase. So most materials go through a thermal expansion process. There are some exceptions in certain directions we will talk about. And in order to quantify this thermal expansion, we have to work in the limit where the temperature change is not way too big and it's a small expansion. So for small expansion, there is a material dependent coefficient alpha, which is telling us the change in length divided by the original length per unit change in temperature. This material dependent coefficient is called coefficient of linear expansion, and with this definition we have the change in the length of a material is equal to alpha times the initial length times the change in temperature. So Li is initial length and delta T is change in temperature. So for most thermal expansion problems, we can use this formula given that we know what material the object is made out of and we can read its coefficient of expansion from a table. For example, here you can see a list of values for aluminum, brass, concrete, copper, etc. You can see that this linear expansion coefficient, average linear expansion coefficient, because it may depend on direction in the crystal, is of the order of 10 to minus 6 per degree Celsius. And there are some remarks about this, some important exceptions. One we should mention is that alpha, the coefficient of linear expansion, can be negative for certain directions in some exceptional materials. So, for example, calcium carbonate. And the other important remark is that if you look at a cavity made of a material, for example, this washer, as this washer is heated, we find that the cavity of the material is going to expand just as if it were filled with material. So a cavity behaves like the material. So we find that a cavity in a piece of material expands as if it were filled with material. So you can find that the radius of this annulus will increase by the same amount given by this formula. Alpha A delta T will be delta A. So as a result of this change in the linear dimensions of the material, we will find that there is a change in the volume of the material, delta V, and similarly there is a beta coefficient times initial volume times delta T, and this beta coefficient is now going to be called average coefficient of volume expansion. So the average over all directions. And it is related to the linear coefficient of expansion. We will find out how it is related. For example, let's say that the initial volume is given by length times width times height. So L is length, W is width, and H is height of the material. And when I heat this material, it has a final volume, V initial plus delta V, and this final volume, V initial plus delta V, will simply be L plus delta L, the new length, the new width, W plus delta W, times the new height, H plus delta H. Okay, so let's take this calculation to the next page. And here I would also like to show you average volume expansion coefficients. They're of the order of 10 to minus 4, 10 to minus 3 for typical materials. Now, I can open this up, so I will find that V initial plus delta V is equal to L plus delta L, which is alpha L delta T, then W plus alpha W delta T, and H plus alpha H delta T. So assuming that I have the same coefficient of a linear coefficient of expansion in all three directions. So this I can put in L W H parentheses. This will be 1 plus alpha delta T cube. So I will find that V initial plus delta V is equal to LWH, or let me write for LWH V initial, 1 plus 3 alpha delta T plus 3 alpha delta T square plus alpha delta T cube by using the expansion of this polynomial. And since we have alpha times delta T is much less than 1. Now, is that really true? So look at these alpha values here. Alpha values of the order of 10 to minus 6, 10 to minus 5. If I have even a 100 degree C change or 1000 degree C change, I will get alpha times delta T 10 to minus 3 or 10 to minus 2, which will be always much less than 1, typically. So basically, because of this, alpha times delta T is much less than 1, its square is much less than 1, its cube is much less than 1. So I shouldn't get rid of this one. The square is and the cube is definitely much less than 1. So to first order approximation, I will find that V initial plus delta V is V initial plus 3 alpha V initial delta T. So V initial cancels, so I find that delta V is approximately 3 alpha V initial delta T, so beta is approximately equal to 3 alpha. And the same argument applies if this is a two-dimensional object. I will find that the average coefficient of areal expansion will be 2 alpha. So similarly, I will find for a change in area in a two-dimensional object, 2 alpha initial area times delta T. So the same argument will apply. Now there is an interesting situation if we look at water. So let's take a look at unusual behavior of water. What is so unusual about it? Let's see. there is an anomaly going on between temperatures 0 degrees C and 4 degrees C. So normally if a water expands as it's heated, its density, mass of the water divided by its volume, as temperature increases, we expect that V increases and density decreases. So if you look at a plot of density versus temperature for water, indeed that is the case, except there is a region here from 0 to 4 degrees C. You find that it is actually density is increasing as it is heated, going from 0 to 4 degrees C, and you can see that better here as it's blown up. Between 0 and 4 degrees C, we have an increase in density, which means the volume is decreasing as we warm up the water. All right, so water expands as it cools. For this temperature range, we find that we find this interesting behavior for T between 0 degrees C and 4 degrees C. Water expands as it cools to 0 degrees C, starting from 4 degrees C. Now that means the density of ice is less than the density of water. So this means ice floats on water because of buoyancy. Ice floats on water, and this makes marine life possible. So if you think about the Arctic Ocean, the surface of the sea is filled with ice, but underneath it, because the ice doesn't sink, this allows the marine life to develop under the water. Now, why do we have such an unusual behavior of water? I'm sure the chemists have a very good explanation. So it is said to be unusual behavior is due to so-called openness nature of the hydrogen bond. So it has to do with the chemical bond in water, which is the hydrogen bond, that is giving us this unusual behavior. Now let's take a look at a few examples. A segment of steel railroad track has a length of 30 meters when the temperature is 0 degrees Celsius. So we have steel, the length is 30 meters when the temperature is 0 degrees Celsius. What is its length when the temperature is 40 degrees Celsius? That's part A of the problem. Well, there will be a change in length, delta L. It will be due to alpha steel initial length times delta T, so that's the initial length. And I have to find out what the coefficient of expansion for steel is, so I can look that up from this table. So I look at steel, so here is steel, here is the average coefficient of expansion of steel, 11 times 10 to minus 6. So I record here that alpha steel is 11 times 10 to minus 6 per degree Celsius. So I find that the change in length will be delta L, which is L final minus L initial, will be L initial times alpha steel delta T, and L final will be L initial times 1 plus alpha steel delta T. So this is going to be 30 times 1 plus 11 10 to minus 6. What is delta T? We're going to a final temperature of 40 degrees Celsius. Therefore, delta T is 10 degrees Celsius. So this is 10. So I find that the final length will be 30.013 meters. So that's part A of the problem. Now part B says, suppose the ends of the rail are rigidly clamped at 0 degrees C so that expansion is prevented. What is the thermal stress set up in the rail if its temperature is raised to 40 degrees C? Now, normally I expect a change in the length from 0 degrees C to 40 degrees C. It is given by alpha L initial times 40 minus 0. So this will be 11 10 to minus 6 times 40 L initial. So there will be a change in length by this amount. Now, however, this expansion is prevented. So I noticed that here I made a mistake because it was raised from 0 degrees C, 30 meters at 0 degrees C to 40 degrees C. Initial temperature is 0, final temperature is 40, so delta T was 30 degrees C. So this is 30, but the answer is correct. Okay, so I have, no, it's 40. Because final temperature is 40 degrees C, I have delta T changing from 0 to 40 degrees C, 40 degrees C. So this is 40 here, 11 10 to minus 6 times 40. That gives me the right answer, 30.013 meters. Okay, so this delta L, which we have calculated in part A of the problem, was 0.013 meters. This would happen, but it is prevented. So when it is prevented, there's going to be a thermal stress building up. So this is a one-dimensional object, so I can look up Young's modulus for this object. For steel, Young's modulus is 20 times 10 to 10 newtons per meter square. So I find that I can use this Young's modulus in order to calculate the stress. Stress is given by force per area. It's Young's modulus times strain. And stress is equal to Young's modulus 20 times 10 to 10 times strain, which is delta L divided by L initial. And what is delta L divided by L initial? It is 20 times 10 to 10. Delta L is 0.013 meters divided by L initial is 30 meters. So I find 8.7 times 10 to 7 newtons per meter square thermal stress building up. So there will be, what does that mean? So there will be a force per area, 8.7 newtons per meter square, building up in this material because we have prevented its expansion thermal expansion. Let's look at one more example. A poorly designed electronic device has two bolts attached to different parts of the device that almost touch each other in its interior. The steel and brass bolts are at different electric potentials, and if they touch, a short circuit will develop, damaging the device. The initial gap between the ends of the bolts is 5 micrometers at 20 degrees Celsius. At what temperature will the bolts touch? And the initial lengths are given here. So I see that I have a gap we're supposed to fill, which is 5 micrometers. I have to read the initial length of the steel, that's given here for steel 0.01 meters. Initial length of brass is given 0.03 meters. Then I have to know the coefficient of expansion for these materials. I know steel here. I can read brass and bronze, they're almost the same, 19 10 to minus 6. So I can write alpha steel is 11 10 to minus 6 per degree Celsius. Alpha brass is 19 10 to minus 6 per degree Celsius. So what I would like to have is the change in steel length plus the change in the brass length to be equal to the gap, so that they will touch each other and the short circuit will develop. And delta L steel is L initial steel alpha steel times delta T, and this will be alpha brass L initial brass times delta T. That will be equal to the gap. And so I will find that delta T is this gap distance, let's call it D, D divided by alpha steel L initial steel plus alpha brass L initial brass. So this will be 5 micrometers is 5 times 10 to minus 6 meters divided by alpha steel 11 times 10 to minus 6 times 0.01 plus alpha brass 19 times 10 to minus 6 times 0.03, and here I find 7.4 degrees Celsius as the answer to this question. So that's the change in temperature, 7.4 degrees Celsius. At what temperature will the bolts touch? Well, that's the change in temperature. So what's the final temperature? T final will be T initial plus delta T. So it should be 27 plus 7.4, 34.4 degrees Celsius will be the temperature at which there will be a short circuit. The two bolts will touch each other. Now you may ask, why don't I consider the thermal expansion to the other side? It's bolted here, so that means just like in the previous problem, we are avoiding thermal expansion on those points. The only way the thermal expansion can occur is for steel to the right and for brass to the left, so that eventually they will touch each other and form a short circuit.